next talk will be coming from Hsiu, our only top on student. So no pressure. It's going to be dust evolution and IllustrisTNG simulation, please.
So first, thank you for the opportunity to maybe give a talk here. And I'm a master student from NTU, and today I'm talking about the dust evolution in IllustrisTNG. So let me first address on why we want to study the dust evolution. So the first thing is that dust is a subject to any feedback process in galaxy. Like all the processes I will mention later, they are highly environment dependent. So if there are any change like in the gas dynamics in the density field of a galaxy, it will affect our dust formation and evolution. So here I mentioned few, and then also the dust will affect our galactic evolution and our understanding of galaxies. So these are the few of the effects it can have influence on. The depletion of metal in ISM, catalyst of H2 formation, interaction with starlight, and also heating and cooling in the ISM. And I will show you some example here. This is a measurement about some galaxies. It shows the metallic depletion from gas phase. That is, some of the metal are captured by the dust, so they are just removed from the gas. So this will change the chemical abundance in the galaxy ISM. Next thing is about the grand catalyst H2 formation. That is, there are three processes that can form a H2. And the grand catalyst is one of the most efficient way to form molecular hydrogen. So if there are any dust in a galaxy, all the process will be dominated by the grand catalyst H2 formation. So it kind of indirectly will affect the star formation in the galaxies. And also that from the previous study by Hsiu, she found that actually the formation efficiency of H2 is dependent on the grain size. That is, if your dust population is dominated by small grain, the formation efficiency will be higher. You can form more galaxies like this one, the right one. And if your grain is larger, then you will be less efficient to form H2. And the last thing is about exchange. It will restrict the galaxy SED. So this is image of Andromeda, the nearby galaxies. So in optical, it seems totally different in optical and infrared. And also from this, so from this purely SED, it's just an illustration that the blue line is the intrinsic SED without any dust. But if there is dust, you will absorb the UV radiation and emit in the IR, so the shape of the SED changes significantly. Then I think this few examples is enough to convince you that dust is very important in galaxy evolution. And so what do we want to know? So first thing is the grain size distribution. It's just, as I mentioned previously, that it can change the H2 formation efficiency. And also it will affect the absorption and the scattering effect in galaxy SED. The second one is the abundance. Like if there are more dust, you will be more likely, the starlight will be absorbed more. And third one is the composition. Then the composition can have several effects, like on chemical evolution or on the also the galaxy absorption, dust absorption. Sorry. Okay, so I will briefly talk about there are 5 main effect processes of dust formation and evolution. So first one is stellar production, and also spiratory. That is, the dust will destroy in very hot gas. For example, the supernova shock. And the third one will be the accretion. That is, you can accrete the gas phase metal. And this process causes the gas depletion in the ISM. the metal depletion in the ISM. And the fourth and third one is, the fourth and the fifth one is the scattering and calculation is the result of the grain collision. So I just briefly mentioned about some environment dependence. So for the accretion and calculation, it often occurs in a dense medium. And for the scattering, it prefers to occur in the diffuse ISM. And for the other two, there is not very significant dependence on the environment density. And for one thing to notice is that the accretion and calculation is the process that will bring small grain into larger grain. And the scattering and spartering will broken a large grain into smaller grains. And then for the stellar production, it will just, this is the process that when AGB star or supernova, when they inject metal into the interstellar medium, some of the metal layer will condense into dust. And through this process, they mainly produce very large dust, very large grains. So, for all this process, they all are depend on the feedback, but the spartering and the stellar production is directly depending on especially the stellar feedback, like the chemical feedback from the stars, and also how strong the shock, the enduring shock will be. They will directly affect our dust evolution model. So I will go into talking on the first result of my research. So I'm going to for the purpose of my research is to understand how grain size distribution evolved in galaxies. And for this talk, I was specifically focusing on the grain size evolution of grain size distribution in Milky Way analogs, the NWA. So what our model can tell? Our model the advantage of a model is to directly calculate the grain size distribution and the total dust abundance. For the composition, we directly taken it from some cosmological simulation, and in this case, it is IllustrisTNG. Yeah. So here we're going to show you what's my research strategy. So first I choose, so I select some galaxies, in this case the Milky Way analogs from IllustrisTNG. I chose the maximum simulation volume, the TNG 300. And I pose some selection criteria here, and for the reason why I want to select the MWA, the Milky Way analog or Milky Way-like galaxies, is that because we know more about the Milky Way, we have extinction measurement. So I can compare the result of my model to the observation. So here is the selection criteria I used. I used this paper, the 2015 paper. I obtained a stellar map. I used the stellar mass and the specific star formation rate as the selection criteria to select Milky Way-like galaxies. And in the end, I have 206 galaxies that have similar metallicity and the star formation rate as the Milky Way, as our own Milky Way. So the metallicity plot is on the right, the upper one. The upper one. This is the metallicity, and the gray vertical line here is the measurement metallicity of our own Milky Way. And the bottom one is the star formation rate, and also again the vertical shaded area is the measurement from our own Milky Way galaxies. Okay, so after I have the sample, I extract the stellar mass, metallicity, star formation rate, gas mass, all this quantity from the industrial simulation, and then put it into my dust model. So let me briefly talk about some spatial specialty with my model. So my model is a one-zone model. That is, I average out all the information of single galaxies. The advantage of doing this is that I can cut down the computation time significantly. And also, because I'm only interested in the statistic behavior of this galaxy, so using one model is okay. And the second thing I do in my model is I try to include gas accretion and also the galaxy merger. From the merger tree provided by IllustrisTNG. Yeah. So that is what that is different things I can do from the previous study. Like previous study only mainly focus on one isolated galaxies. So after I have a dust model, I put it into a model and then get the data and then analysis. So how do I analysis? So as you probably know, that the grain size distribution is not an observable quantity. So what I can do is I calculate the dust. Okay, so I calculate the dust abundance by summing all the dust like under this grain size distribution area, under this area, and get the total dust abundance. This was measurable. And another thing is I calculate the wavelength dependence extinction curve based on the main theory. Like we calculate the extinction and we calculate the shattering and extinction effect only based on the dust composition and their grain size distribution. Okay. So here I'm going to present my result. So first I will first validate our model with the nearby mission of dust metallicity scaling relation, and then I will show you the evolution of the grain size distribution and the extinction curve. So first is the validation. So on this class, the color dot is our calculation result, and the gray dot here is the measurement from some nearby galaxies. So as you can see, our model roughly cover this range that is consistent with the observation. And as you may notice that there are some galaxies at this region, and although it seems that it's not consistent with the observation, but it's only a minor fraction of the overall population. So we, in our analysis, we just neglect them. Yeah. So overall, it consists with observation. That is the most important thing. And then is the evolution of grain size distribution. So here I show you the grain size distribution statistics result of the grain size distribution over these 206 galaxies. The solid line is the median value and with the dispersion. So I only start from the registry. Here the dust is dominated by large grain dust. This mainly come from the stellar production. So the stellar production will dominate the early time. Yeah. And later, as the time goes on, the small grain will increase due to the accretion, shattering, sputtering, and also calculation effect. It will go on, and you can see this peak at redshift 1, and later it decreases a little bit. So there are two things I want to mention here. First is that our model reproduce our model roughly cover the so-called MRN slope at redshift 0. So this MRN slope is some empirical slope measured in 1977. I would believe this is the significant grain size distribution of our own galaxies. Yeah, so yeah, we will say that roughly cover it with the dispersion. And the second thing I have to mention is, like you may already notice, this is the green curve. Actually, they have a small dispersion at ratio 0. redshift 1. And we saw that it's due to the chemical evolution and also the gas content, the gas evolution in the galaxies that reach some kind of equilibrium at redshift roughly equal to 1. So, and at that, after this spatial time, we the diversity of the metallicity in galaxies and also the gas content drift the brain size distribution away from the equilibrium. And so at this point, like the most significant difference between redshift 1 and 0 is that this bond is decreasing from redshift 1 to 0. And this is caused by the shuttering calculation effect, and which depends on the ratio of the dense and diffuse ISM. So, yeah, in IllustrisTNG, actually they do not well resolve the dense ISM. So that probably this offset, probably due to the unresolved things, we cannot make sure about this, or we can test it in some future, maybe future more high resolution simulation. Okay. So after we have the brain size distribution, we can calculate the extinction curve. So okay, so this dark blue dot is the measurement from 1992, the Milky Way extinction curve. So as you can see, our model successfully reproduced the bump here, this bump, and roughly our extinction curve roughly cover the mutual extinction curve at this long wavelength region. And although our model gives a steeper prediction at the short wavelength region, and that's we are trying to working on it. And so that's my result. And in the end, I will bring you some current challenge of our model and also the dust evolution simulation things. The first thing I will mention is about the dust geometry that is important on the galaxy FED, and I will show you an example later. The second thing is about the brain size distribution actually will be different in different regions in the galaxies, and I will also show you later. And the third thing is, in our model, we have a very simple model on CJ inflow and outflow things, but it's quite simple. It just is some scaling relation to deal with this kind of things. And if we want to study more on their inflow and outflow effect on the dust evolution, we have to move on to maybe some spatial resolve simulation. So here I will show you some dust geometry effect. That is when one of the examples is that the attenuation curve, extinction curve, actually will depends on how many fraction of the star is covered by the dust. So if you have more dust around the star, you will get more attenuation. But you have less dust, you will get the lower one, the less attenuation one. Yeah, that is the thing we can only do in spatially resolved simulation. And also we have to do this with the help of radiative transfer code. And that is what I can do in my current model. And the second one is, I will like to remind you, is the brain size distribution is actually vary from galaxies. Like this is a simulation conducted by Oyama in 2020. He directly implemented the brain size the brain dust evolution code into a hydrodynamical simulation of an isolated galaxies. So in his work, he found that at the inner region, the blue line, the extinction is not like significant at the short wavelength region, but for the outer region, the green and the red line, you can see the steeper extinction line here. Yeah, so I haven't checked like how will it be if we sum out all the extinction things to the average all the extinction to one single galaxy. I'm not sure about that, but just remind you that the spatial the grain size distribution will actually different from in different regions in galaxies. Yeah. So to sum up, so for my own research, I implemented the post-process model on TNG, and also validated it with the dust metallicity scaling relation. And our model really reproduced the MW extinction curve. And also, I have to remind that the strategy and calculation are important to recover a Milky Way grain size distribution. And also that, there are some challenges here, and I would be happy if I can solve it one day. But yeah, that's currently I can for now. Thank you.
Start questions for you, Hsiu.
So if I understood correctly, so when you compare this dust size distribution with different redshift, so that basically you are taking different snapshot from this TNG simulation, right? And then you do this random model to calculate this dust chemical network to get some equilibrium. So is that correct?
Yes. So maybe go more precisely, actually I put. Actually, I put initialize. So this is the merger tree of IllustrisTNG. So I initialize it's the high redshift n. Then initialize the dust size distribution. It's a high redshift n, and let my dust model evolve through this merger tree. Yeah, and what I show on the grain size distribution is the grain size distribution at this main branch.
So basically your model also evolve in time.
Yes.
But you consider maybe the density information from this merger tree.
Yes.
So can the dust also be destroyed?
Yeah.
During this evolution?
Yes.
Like
sputtering, like in our ring break down the large particle from some size of the particle, it can just totally destroy it. And also our assumption, one of the assumptions is that for any outflow of the galaxy, we simply assume that those dust like going into the region will never go back. Even though they will actually, in fact, they will come back to a galaxy with the inflow, but the inflow gets it too hot, that will probably destroy most of the dust. Yeah. But that is just our simple assumption of these kinematics.
So, follow-up question. So, what do you use for the initial condition for the dust grain size?
I think okay. So initially, I just I think I assume an empty space, and because at the beginning there are no dust presents, so like most of the dust process do not happen. The only things can happen is the stellar dust production. So the empty space will only grow up in the large region and turn and as a function of star formation rate, and also mainly as a function of the star formation rate.
Did you have to assume some microphysics parameters for the coagulation and shattering?
Yes.
And is your result sensitive to this kind of
Our result, well, it depends on part. The part is a little bit maybe okay. So they will change, but the most sensitive things is how many dense gas is in the galaxies. That contributes the most to our data. So like all the other microphysics does not change a lot as much as the dense gas fraction.
Any more questions and comments? I got a few. On the decrease of the abundance of the large grain size from redshift 1 to 0, where did it go?
Actually,
Eight.
so I follow the so there's one.
Because there's no increase in any of the other size, there's only a decrease.
So I presumably we saw like it just be destroyed or going into the CGM. Because at this moment we also observe the decrease of metallicity in our TNG sample.
On redshift 1 to 0, there's a decrease.
After 1 to 0, there's overall shift of a decreasing.
Metallicity? Oh.
And also the density factor also changes this moment, like it grow up a little bit. So it will. So if we enhance
The metallicity means gas-phase metallicity?
gas-phase metallicity.
That's sort of contrary to the observational evidence, right? Usually it's growing,
Yeah.
so but you don't see that.
Cold gas phase, right?
And yeah.
This gas. So
The cold gas, right? The metallicity, gas-phase metallicity is from the ionized gas, I guess, from,
you're talking about increasing,
yeah, the increasing by measurements, the cathode gas. Okay.
In simulations, you tend to see that kind of flat line, the low redshift, because you're predominantly increasing relatively low metallicity gas.
Not that means
Established.
So it is a merger actually affects the resonant wash.
So I think this part, with this decreasing in the redshift 0, it did not seem in a previous isolated galaxy simulation. So, but I cannot make sure like which part contributes it. So one thing is the interaction between the galaxy and the CGM, and also the merging may also take part into this.
If you have this history and you deploy time, can you, for example, make a movie, see how it evolved time, see if they are corresponding to some
Yes.
event?
Yeah, that would be a possible way to do it.
Guess you should talk to Ken.